Okay, in this short little video, I'm going to prove some wonderful facts about the Fibonacci sequence. Well, really just one, and it'll give us some practice for thinking about Fibonacci sequences, thinking about recurrence relations, thinking about induction and summations, and so it'll get us practice on a bunch of powerful tools for discrete math. All right, so here is the Fibonacci sequence, in case you forgot. The Fibonacci sequence has numbers. It starts with 0, then 1, and then every number is the sum of the two previous numbers. So 0 and 1 is 1, 1 and 1 is 2, then 3, then 5, then 8, 13, 21, 34, 55, okay, etc. It goes on and on. And again, you can see that each number is the sum of the two previous numbers. All right, 21 is 13 plus 8. Okay, so this is our Fibonacci sequence. And if we want to write it out as a recurrence relation, we would say that f0 was 0, f1 was 1. These are the base cases. And then fn is equal to fn minus 1 plus fn minus 2. That is our Fibonacci sequence. I can use the Fibonacci sequence to make another sequence, and I'm going to call it G. So I'm going to define Gn to be equal to the sum of the first n Fibonacci numbers. So this is the sum for I in the range n of fi, and this right here, when I write a number in brackets like this is shorthand for the set that starts at 0 goes up to n minus 1. So it has n elements in it, and so that'll give us their first n indices. And the theorem I'm going to prove is that I claim this is equal to fn plus 1 minus 1. Now, I've told you the punchline here. I told you what I'm going to prove, but if I just wrote down the definition, we could have perhaps guessed that this was going to happen. And the way we would do it is we would just try to write down some values of G. For 0, there would be 0 elements in the sum, so that's an empty sum. It has value 0. If I summed just the first Fibonacci number, which is 0, the sum would give me 0. Then the first 2 add up to 1. The first 3 add up to 2. And I can continue on this way. What do I get? The next one is, if I add the first 4, they 1, 1, 2, that's 4. Okay, and if I add in the 3, I get 7. If I add in the 5, I get 12. Plus 8 is 20. Plus 13 is 33. Plus 21 is 54. And we can see that I just drop 1 and I reduce the index by 1. So 8 minus 1 is 7, 13 minus 1 is 12, 21 minus 1 is 20, etc. And so I might have just written this down and kind of observed this pattern that there seems to be this relationship as we go. Now, after doing that observation, though, I come up with this conjecture, and I want to prove this conjecture is true. And I'm going to do it 3 different ways. So the first way to prove this theorem, which is, again, that g of n, the sum of the first n Fibonacci numbers, is equal to fn plus 1 minus 1. The way I'm going to prove it is just by induction, which is a pretty standard approach for many such problems, especially where you're given the value of the sum. You don't have to discover it yourself. You just need to check that it's correct. And so the way I'll do this by induction is I'll do induction on n. And so I'll check the base case, which is that n equals 0. Then we have g0 is an empty sum, so that's equal to 0. And that is also equal to f0 plus 1 minus 1. So just to double check here, this would be f1, which is 1, and 1 minus 1 is 0. So I've written it, I've shown that for n equals 0, it has exactly the right form. Okay, so our base case is settled, and so now by induction we're going to assume that for all k less than n, that gk is equal to f k plus 1 minus 1. All right, and to do this now, I take gn, which by definition is this sum, and I pull off the largest term. This is a pretty standard technique for many summations where the closed form is verified using induction. So I would pull off the largest term, and what I'll get is a gn minus 1 plus that last term, which was fn minus 1. Now, using the induction hypothesis, I can now claim that this gn term will be equal to fn minus 1. So that's fn minus 1 plus the fn minus 1. I'm trying to articulate my speech here to make it clear where the parentheses are and what's in the subscript and what's not. So this leaves us with two terms that we know what to do with, right? There's an fn and fn minus 1. When we add them together, they get fn plus 1, and the minus 1 is still there. Okay, so this is exactly the thing we were trying to prove, and so we're done. We've shown that gn is equal to fn plus 1 minus 1. Now, that's one way to do it. Here's another that will seem a little magical. I'm going to use a pretty powerful fact, which is that the Fibonacci numbers have a closed form. So I can write the following. I can write fn is equal to phi to the n minus psi to the n over square root of 5, where these numbers phi and psi are, phi is the golden ratio, so it's 1 plus square root of 5 over 2, and psi is the conjugate golden ratio, so it's 1 minus square root of 5 over 2. And these are pretty special in that they satisfy the following equation. So if I take phi minus 1, I get 1 over phi. And similarly, psi minus 1 is equal to 1 over psi. Or another way to write this would be, maybe even better for our purposes, would be to write that 1 over phi minus 1 is just equal to phi, and 1 over psi minus 1 is just equal to psi. And we'll use this in a second. So now I'm going to reprove our same theorem, which was that this new sequence gn, which is the sum of the first n Fibonacci numbers, is equal to fn plus 1 minus 1. Okay, so the proof goes like this. I have g of n, and it's equal to the sum of the Fibonacci numbers, and I'm going to plug in the closed form for the sum. And at first, this is going to look like a mess. It's going to look terrifying. At least I think it should. So this is phi to the I minus psi to the I over square root of 5. Now, it looks hard to deal with, but we do have some standard things we're allowed to do with summations. For instance, we could take this square root of 5 and pull it out, because that's just the distributive law of multiplication. We can also take these two different terms, because they're just being subtracted here, and we can break it into two different sums. So when I apply these tricks, what I get is 1 over square root of 5 times a sum of phi to the I minus the sum of psi to the I. And the reason this gets us some progress is that we should know what to do with these, because these are just geometric series, and there's a closed form for any geometric series. It's equal to the following. We'll have, this will be phi to the n minus 1 over phi minus 1, and that'll be minus psi to the n minus 1 over psi minus 1. Okay, so each of this geometric series gets expanded out like this, and now we can use this fact we pointed out before, which is that 1 over phi minus 1 is just equal to phi. So I can expand this out, and what I'll get is 1 over square root of phi times, this will be phi n plus 1 minus phi minus psi n plus 1 plus psi. Now, reordering this, pulling off the terms, the n to the 1, or n plus 1 terms here, and the other terms separately, what I see is I've got phi to the n plus 1 minus psi to the n plus 1 all over square root of 5 minus phi minus psi over square root of 5, which, according to this fact we have sitting here up here at the top, that means that this is just fn plus 1 minus f1, which, well, since f1 is equal to 1, that's exactly what we were trying to prove. But I'm going to leave it like this because it hints that there might be some other way to derive this closed form. See, when you have an expression like this, where it seems like a subtraction of a term at the end of a sum minus 1 at the beginning, that's the kind of closed form you get when you had a telescoping sum. So maybe we could have written this right from the beginning as a telescoping sum. And so this will be a third way to prove the same fact, and I hope it will be your favorite because it takes this definition of the Fibonacci numbers, the recurrent part, which I'll write now for fn plus 2, and it uses it to rewrite fn in a way that will telescope when I sum it. So here's what I mean. I'm going to take this equation, and this is equivalent to me writing fn as fn plus 2 minus fn plus 1. And so, again, my theorem was supposed to be that the sum of the fi's, the first n of them, is equal to fn plus 1 minus 1. I'm actually going to prove something even stronger. Rather than just summing the first n, I'm going to sum over a range. So I'll sum over the range, let's call it a to b. And I'm going to get that it's f of b plus 1 minus f of a plus 1. Now, if you're not familiar with this a to b, this is the set a plus 1, etc., all the way up to but not including b. So the number of elements in this set is b minus a. Right, so we will get the other theorem as a special case just by plugging in a equals 0. All right, so how do we do this? I guess we just need to write the sum and then replace it with this other equivalent form. So I write a to b here. This is equal to, by this fact, it's equal to the sum from a to b of fi plus 2 minus fi plus 1. All right, so what will this give us? If I were to write this out, and let's say I started with the largest terms, the largest term here is I equal to b minus 1. So b minus 1 plus 2 is b plus 1. And then I plus 1 would be just fb. So that's the largest term. And then the next one for I equal b minus 2, I'll get fb minus fb minus 1. And it will continue all the way down to the last term for I equal to a, and I'll get f a plus 2 minus f a plus 1. Now this is standard telescoping sum, so what we'll see is that each term cancels with the term in the next one, And all that's left will be the very first and very last terms. And so that comes out to be just f b plus 1 minus f a plus 1. Okay, so when you get comfortable with these telescoping sums, you'll recognize that this is really just really how it always works out, that you're going to sort of plug in A and B in this way. And again, if you haven't seen this before, if this looks like or smells like the fundamental theorem of calculus, this really is the discrete analog of that fundamental theorem of calculus. And so this gives us a third proof that the sum of the Fibonacci numbers gives us another Fibonacci number minus 1, but also this version lets us sum over other intervals, which is handy.